So, hi everyone. I'm Brandon Ribick. I'm the technology director at Numerical Makes, and welcome to the virtual game day. We're going to be talking about the quality made today. And as I was kind of starting out by just reflecting a bit on kind of where we started with this journey about 5 years ago now, of when the opportunity for quality made first came out. And so I'm really excited to be here today, and myself, I'm sure you are all as well, to learn about what we've learned over the last several years with this program and how we've become more familiar with not only model-based approaches and these various digital tool sets and how they aid the qualification journey for additive manufacturing. So I'm sure we're all excited to learn together about the progress that's been made as well as how it can influence our future decisions. So I'm really thrilled to be here today. I'm so grateful that we had the opportunity to host this conversation. And so with great pleasure, thank you all for being here. I want to encourage everyone to ask questions in the chat. There's a chat function here. It's available. We'll be doing a bit of Q&A as the presentations go on, and we'll be having a roundtable discussion after the projects are presented. But I wanted to welcome Program Officer from the Office of Naval Research, Jen Wolf, to the stage. I'm great to have her today to open up the conversation and really start the ball rolling. So, hi, Jen. Good morning or good afternoon.
Hey. Yes, I know. You just crested the afternoon mark. You know, your computer needs a little extra coffee there for your audio, usual stuff. Yeah.
Of course.
It's okay. I got we switched IT servers, so it's an adventure.
Absolutely. So welcome. The stage is yours. Thanks for being here.
All right. Thanks so much. Hey, Tara, can you pop up my my slide for me real quick? And while the slide's coming up, just want to say hi, everybody. It's a great pleasure to be here today to really talk to you about quality made. And quality made is the formal name of this program is Quality Metal Additive Manufacturing. And really, what we're looking to do is to change the paradigm of how do we do qualification and certification. We have all been through the challenges of really trying to figure out, in the world of additive manufacturing, how are we going to build things reliably and repeatably to ensure that we have structural part performance. And so when we really look at conventional qualification and certification, it's predicated on hundreds of test coupons to ensure that we have material that's reliable, we understand the performance and those properties, and we have process repeatability and reliability. And we lock it down to ensure that structural part confidence. But additive manufacturing allows us agility. It allows us the flexibility to change things, right? To go from an aluminum one day to maybe a different aluminum alloy another day, right? And so if we want to be able to take advantage of agility, we need to be agile in how we qualify something and agile in that kind of understanding. And so Brandon alluded to this before, that it was like 5 years ago when this RFP first hit the streets, right? And I'll fully admit it was a challenge to convey what we were trying to do and how we wanted to look forward in changing that paradigm, how we envisioned the ability to couple integrated computational materials engineering with the ability to control and sense and really provide insights into that structural part confidence. And so it's been a long road. I'm also not gonna lie, along this road, I really didn't think there was gonna be like a pandemic along this path either, right? And so kudos to my team for overcoming a lot of those challenges. I'm so excited for y'all to hear about the progress that has been done, about how we have built a framework for rapid qualification certification. You will hear about some very cutting edge modeling advancements in sensors and process controls, and really how we can better inform our processes moving forward and how we can think about things a bit differently. So recognizing that, you know, we have today our colleagues from GE Global Research, from Lockheed Martin Space Systems, as well as Concurrent Technology Corporation. So with that, I'm going to actually turn this over a bit early to those folks to really be able to give you a lot of those details, to give you insights into what's going on. Okay, so Tara, I promised you I'd be done real fast to give some more time for the technical meat that is to come. So with that, I'm going to hand it back over to you. I will be on also for the roundtable discussions and available over chat, but I'm so glad folks are able to tune in for today.
Hey, Jen. Hey, do you want to introduce Eamonn and then I'll call him up on stage?
Sure, that sounds great. So the first one up is Eamonn Salam from Materials Resource LLC. He is supporting Mike Timms from Concurrent Technology Corporation. Eamonn, I know you have a ton of slides for you to go through. If things are as they usually are, it has been a pleasure working with this team, as I'm sure Eamonn will cover in the next go round. They are focusing in on 316L as well as 17.4pH. So, floor is all yours, Eamonn.
Thank you so much. Just a quick sound check. Can you hear me and see the slides?
Yes.
Excellent. Thank you. Thank you for the chance here. I am proud to represent a team that Concurrent Technology is the prime, and we are a subcontractor to them. And myself as the PI, and Mike Timms from Concurrent Technology, the program manager. And thanks, Jennifer and the Office of Naval Research for giving us the chance to work with that. Our team member include MSC Software, as well as SLM Solution, and University of Pittsburgh, and America Makes. And we are looking at implementing Icme, Integrated Computational Microstructure and Format Response Tools for AM parts. The whole idea, and we start with the bottom line up front, we like to provide the Navy with the ability to rapidly produce and qualify low volume metallic parts, mainly using commercial off-the-shelf laser powder bed fusion machines, integrated with our Icme tool set, and as well as integrated with numerical simulations and providing the data associated with that through a very robust data management tool to enable them to have what they need for qualification of the parts. And with that, there are three items I'd like to highlight today. The first one, we will demonstrate to you the Icme-based systems on a Navy component, an actual component that we got public release to share with you. And then we're going to share with you what we are trying to do to confirm repeatability and reproducibility at the component level, looking at strength and fatigue behavior. And at the end, we're going to share with you our path for technology transition within the DoD, ONR, DoD, and also the larger audience in the OEM side. Our team, as I shared with you, This is the infrastructure of the team, ONR, the stakeholder, and other Navy team members as well. CTC, the program manager, MRL is the principal investigator, and the rest of the team, MSC, SLM, and University of Pittsburgh, and America makes. Even each one of us is responsible for one piece of this big puzzle that we are trying to solve together. And our approach it can be focused in, then we are integrating the cyber domain within the multiple modeling and simulation tool within Icme framework with an AM process, laser powder bed fusion, with the COTS machine SLM280, which is our physical domain, as well as the characterization methods that we are integrating it with the results coming out. With that, the steps we took is to link microstructure to properties and performance. And we utilize an FEM solver, SimuFact in this case, with multiple modeling and simulation tool to incorporate the material behavior within the FEM solver, as well as within the property predictions. We utilize our commercial tool, ICAM, Integrated Computational Adaptive Advanced Manufacturing Toolset, to link microstructure properties, defect and distortion predictions, as well as looking at both static and dynamic behavior of the material. We are integrating with SLM280 that comes with two unique sensors, the mill-pole sensor for mill-pole monitoring and the laser power monitoring as well. And we are integrating the tool to utilize the sensors data for defect detection that we are using the modeling to infer what are the sensors are predicting for us. And at the end of the day, we're going to develop a full integrated system that we're going to deliver to ONR by the summer time frame. The overall idea of the process, this is a very busy chart, but I just want to give you the lay of the land of what we are working through. The rest of the team, you can look at that as the table of contents. So it starts from the top right corner when you get a CAD. Then we utilize our tools to identify what under in-service loading condition, the most critical area. And we identify what we call the region of homogeneity, which is simply we utilize some machine learning tools to identify the clustering within a large feature vector that include the microstructure, the defects, as well as the external loading condition. Then we feed that at the most critical area, in this case will be the red area. We use the work with integration with the SimuFact to identify the thermal profile using a hierarchical simulation that I will share with you later on. And from there, we call the ICAM database and models to predict the microstructure as quantified by the two-point correlation, the orientation distribution function, and the defects. We have a quantification for it that will takes into account the shape and the morphology and the spatial distribution. Then we feed into our fatigue life prediction models that are able to predict an S-N curve that we validated, and will show you the validation throughout the process, as well as the anisotropic yield surface in the location of choice. And then we utilize this information to help to optimize the orientation of the build itself. And once that's optimized, we can have an additional tool to do topology optimization, and you are seeing the part after topology optimization. Then we send it to the machine that give us sensors data as well as build information, and then we produce the part and then later on machine it to specs. Going through this quickly the integration with the machine is the item I like to share with you. This is the current activity that we are working on it, and this integration is taking three main steps. The first one, we were integrating with them on the single the total uncoupled method is what we call step number one, where we are talking about the cloud data analytics. They send us information, we analyze it, and we link machine parameters to simulations to sensors data. And then the fog data analytics, where our machine will be taking information on layer by layer cases, and we are in the middle of working on this. And then the end of the day, when we are dealing submitting the machine and delivering it, we will be working on the edge data analytics, where the analysis will be done on our computer connected to the SLM machine on site with the Navy. And with that in mind, I wanted to share with you quickly, and the image is a little bit stretched. For this case study is made of 316 L part, that the whole idea is, if we're going to do one or two of this component, we don't have the time or the money to make 100 of those and test them. If we're going to do one of two of this component, how our predictions will enable us to understand the location specific fatigue behavior as well as static behavior, and how that will identify the factor of safety related to it. And we are looking for the yield strength. The factor of safety will be 2 or at least or better, as well as the fatigue behavior. We are looking to reach 10 to the power 5 or higher. These are some of the examples we could be looking at. So what we are looking here to understand some of these fundamental questions that we'll answer it through the next few slides. When we are producing this part in SLM 280, can I build the two parts at the same time? What would be the build orientation? What type of machining should I have, and post-processing, heat treatment, and should I have or shouldn't I? And when we topology optimize it, how it will look like. So this is a quick slide showing the part in service, and literally how after we produced it, machine it as a solid, as well as after topology optimization. And we did the prediction for the fatigue and the static in advance. And then there is blind testing experimentally done by CTC team, where they took the part, cut it in pieces, and compared our prediction of fatigue, tensile properties, and microstructure morphology, crystallography, and the pore size and distribution. The kind of slide you see in front of you is the STL that we built at CTC on their machine with our optimized build orientation, as well as support structure that was for additive manufacturability, and later on actually also for machinability of the part. Some of the things you see, some of those features are related to how it will be easy to machine it later on. And the details we did it, we identified the most critical location as what we call the region of homogeneity of the feature vector that takes into account the microstructure variability, and as well as the resolved stress tensor. And we looked at the area and we focused on this area to find the best fatigue behavior. And with that, we put it in a relationship with the gas flow. And I have a quick slide later on to show you how we have a virtual chamber that allow us to take into account the gas flow and the soot, as well as how we are designing certain holes that can be later on easily machined, and how we choose them, with the distortion, how we maintain cylindricity of the part. The countersinking that you saw was intentionally designed to guide the tool to do the machining later on. And the support structure also to control the distortion, and also to be able to machine it later on with some wire ADM with minimum misalignment of the part. The test plan that you see on slide number 10 is showing the location that we choose as a team to pull fatigue samples as well as tensile samples. And for every one of those locations, we had predictions of the fatigue life, and as well as the tensile behavior of the material, as well as microstructure. Then Mike Timms from CTC later on took this data and compared it with the experimental measurements through a blind test that was shown to the Navy later on. Going through the whole slides again, you can see we're going to quickly take you through the process. Now this is the outline, and the first thing, as you see in slide number 12, when we did identify the most critical region under the in-service loading condition, and what we define at the region of homogeneity. And here was looked at the whole stress tensor. It is the 3x3 stress tensor, and not just the von Mises value. And with that, we have a machine learning tool to identify the region of homogeneity is based on the whole stress tensor. And it is generic, therefore it can be used in other parts generically, not just this part. And following slide number 13, you see our use of SimuFact tools to be able to predict the location-specific thermal profile as a function of the scanning strategy and the machine setup, including even the laser diameters, and the calibration that we did in-house with the hierarchical simulations at the melt pool level, all the way to take into account the material behavior at higher temperature, not just at lower temperature, and then the location-specific prediction of the thermal profile as a function of multiple layer that was added. And the hierarchical simulation that you're seeing in the screen right now, in the far left, we are capturing the material behavior at the single track level, and where we're taking into account the morphology of the melt pool and how it is related to the morphology of the solidified melt pool. And we utilize a unique trick that we developed at MRL. Then SimuFact was one of the few FEM solver that implemented is what we call crystal tracking. So instead of handling the whole FEM mesh, we are able to sample it, and some of this information is in the paper that is referenced in the bottom. And then we take the information at the single track and we go to the single cube, and as you can see, we are keeping track of the scanning pattern, and we have multiple methods that we are training our models to speed up the simulations drastically. And again, we utilize the crystal tracking as well as looking at the region of homogeneities within the part to transfer the thermal information from the single track to the single cube and later on to the single part. And you are seeing the single part now is being built on a layer wise, and the information is fed at the layer level or at the region of homogeneities that allow us to capture the thermal profile in various locations and the most critical location that help us to predict later on the microstructure as well as the post-processing that we will need to do later on. And with the information was used with SimuFact to predict the residual stresses, and this is some of the orientation that was selected. We covered the 360-degree available orientation, but from those selections, we were able to predict that the maximum distortion in one of them was about 1 millimeter, but we were able to get the part to have the least amount of distortion as well as the least amount of machining that required, and that's the part in the middle. That's what you saw in the prior slides, how we are able to build it. From the post-processing level, this material is very unique, and instead of going with the conventional heat treatment approach, we have developed at MRL through another funding from NavAir an optimized heat treatment for this alloy that allow us to provide properties that exceeds the performance of flat alloys. So you can see we control the cellular structures, and we have to look at the residual stresses and the crystallographic orientations. And with when we implemented this heat treatment, we're able to optimize the behavior of the alloy with this new heat treatment, and that's what you will see in the results in the few slides. What you will see in slide number 17 is comparing the as-built condition with the conventional stress relief process, and then with our stress relief approach. And you can see we wanted to demonstrate it in the standard cantilever. And you can see the heat treatment approach that we developed at MRL resulted in less than 0.1 millimeter distortion in the cantilever. And with that, we calibrated the models that we fed into SimuFact to be able to utilize this part for optimizing the build orientation to take this heat treatment through the process and optimize the build orientation with it. This is the implementation on the actual part of this information, and when we are developing it, we are able to any arbitrary shape, and we are using an optimized inherent strength tensor that take into account the scanning strategy and the thermal profile, and allow us with that one to see where is the location of the highest residual stresses. and the highest distortion. That's even before the implementing our optimized heat treatment. Some of the things to show during the blind testing is comparing the texture in the region of homogeneity, of the critical region of homogeneity, predicted texture to the measured texture using the samples that was identified in the earlier slides. And you can see we pretty close when you are comparing the prediction and the measurements. And since we utilize the orientation distribution function, we are able to do the comparison quantitatively, not just qualitatively. Similar location on the 1-1 pole figure, similar, very comparable intensities, small variation in the 001 pole figures, but the intensities are comparable and within the expected variability of the experimental texture measurements. And you can see these are the area that we are highlighting in the slides here. And it is, for both of them, is still considered a very weak texture. And now this is how the measurements of the texture to show you also the micrographs as well, the inverse pole figure maps and the measured microstructure that we were comparing with the predictions. And I wanted to confirm to everybody, we are not predicting the spatial information about the IPF map. We are predicting the ODFs to represent the texture information. And when we wanted to talk about morphology, we use our higher order statistics, and those higher order statistics allow us to use two-point correlation to compare predicted as well as measured morphology of the grains. And then we use a modified line intercept method, we call the chord length distribution, that you will find both of them in the earlier paper. And what you can see, we were pretty close in the morphology as defined by the orientation by the two-point correlations. We have some tilt that could be due to the cutting of the samples, but the volume fraction as well as the morphology as identified with the two-point correlation, we're pretty close. We have dimensions of the grains, we were close enough, but this is part of the extreme measurements, and our prediction the little slightly different than the measurements. But when you are looking at mean behavior, you rarely take into account the maximum. So our mean is pretty close, 51 and 49, and our spread is pretty close between them. The maximum is that we can use later on extreme value statistics to define it. When it comes to looking at the predictions of the defects, and this is the trickiest one that we are looking at the material, where we are using a machine learning tool to predict the box plot. So what you're looking in the bottom left corner, this is the measured box plot, and we have predictions of box plots as well, which is the statistical information about the defects that feed into the fatigue model through extreme value statistics. And one of the important things, all this measured was done on coupon samples that was extracted from the core of the part at the pre-selected location that we demonstrated earlier to everybody in the first cut of the samples that we did, both the measurements and the prediction. The part of the solicitation of this project put a goalpost for us of comparing prediction and measurements, and that goalpost is what you see on the screen, slide number 23, where we were comparing with cast and wrought, and we were expected, we needed to be within a certain tolerances between the threshold and the objectives, and we'll show you how we be comparable to this. But this is where we are looking for repeatability and reproducibility of the data that we are doing it, and that was confirmed with the blind test. So we did a lot of simulations and predictions and Bayesian inference, and then the results was compared with a blind test, and we did multiple experimental measurements that we'll show in the next slides. So the first thing, for example, what you're looking at that slide here, The fatigue testing, we did intentionally fatigue testing at 320 megapascal, which was a lot higher than the yield strength of the material, both cast and wrought. So you can see from literature, and we wrote the literature information and the MMPDS S-basis information for the same material. And you can see we fatigue tested the material at even above the wrought properties that you are able to see it in the screen. We'll show you in the next slide how we met and exceeded wrought properties in this material. So we did be able to get stress at above the yield, 230, and when we are hitting the yield strength of wrought, we had runouts. The yield strength of the material, the predicted versus measurements, we were about within 5% difference, as well as both in the build direction. When we reached UTS, we're within about 3% between predicted and measured. When we came to elongation percent, and this has been the Wild West everywhere, is just due to the current parameters requires a lot information to predict the damage, which is related to the elongation percent. This is where we were a little bit outside of the range, but knowing this material is not expected to be plastically deformed. The approach that we are sharing with you doesn't only apply to SLM. We applied the same approach in other machines. We applied to 3D systems, and we are in the process to apply it to ES machines, and we have a plan also to apply it in RCAM machines. One of the holy grails are related to fatigue, and this is where we are showing you the prediction that we have for the material, for the vertical and the horizontal. For this material, this is the machine, and you are able to see when you are looking at the yield strength for wrought or cast, we are able to test above wrought and cast, about 125% higher than them. And we were able to predict 10 to the power 5 compared to fatigue life at that stress amplitude, which is 320 picopascal, using the heat treatment and the build information that we provided to you. One of the interesting things we like to share with you, when we did the predictions, it covers both machined as well as knit shape material. The difference is where the defects is. So the machined and electropolish, it was embedded defects. The knit shape was mainly related to surface defects, and the dotted model cover the work that prediction we did it for the knit shape, which is mainly related to surface defects. And then one of the testing that was done by CTC looked at having one of the samples that results in a totally out of the repeatability. So you can see the spots here showing you the repeatability. Then we have one sample was an outlier. And in a blind test, we predicted that this sample had an anomaly on the surface because it met more closer to our surface defects more than our machine surface. And when we got it, we discovered, in fact, the machine did not pass initial inspection, and it did have indeed a surface defects that we are confirming here. And that was another unintentional blind test. The prediction for the anisotropic yield surface, as we showed earlier, within about 5% of the experimental measurements. And we utilize a lot of comparison of the sensors data with the data that we generated in-house in prior sensors work, and this is work in progress. What you are seeing here is how we calibrated our machine learning tools using work we do it with the Defense Logistic Agency. This is our in-house sensor that is used to also utilize it to train our tools on the sensors from SLM, the multiple monitor. And what you're looking at is a cube that with intentional defects, and the left is our the measurements that we did with the multiple monitoring for the photons with the diodes. This is comparable to what expect with SLM. In the right, you see our micro CT that's comparing. We nail down location-specific defects comparing sensors as well as micro-CT, and this is how it looked like in 3 dimension. We call this is the calibration build cube for sensors. And when it comes to try to compare the data and share it with others, I will share with you in the last 3 minutes some of this browser-based tool that we have, a virtual chamber that we're able to control at the part level, at the region of homogeneity. We're able to show the information, both prediction as well as experimental. By the end of the day, we're going to deliver to the Navy the SLM machine with the Icme, the Icam software with MSC tools, and the plan is to have them integrated together, that it does not require a PhD to run it. A technician will be able to run the tools and build it based on an optimized behavior that will be targeted fatigue as well as static loading. And with that, I will ask the moderator if we have 2 minutes to show the demo of the software, or I can open to questions. I'll leave that to the moderator. Thank you.
Well, Eamonn, as always, I'm always impressed about how much you can pack in just sheer quantity of slides. Okay, so I think we have a bit of time, maybe like 2 minutes to go to your live demo piece, because you have a bunch of questions in this chat that we are not going to be able to get all the way through. So I'm going to, so I'm not going to lie, for the audience here, if you upvote the question, it's probably more likely to get answered in our current time constraints. Wow, that was a very fast turn on upvoting, folks. All right, so Eamonn, while you do your quick walkthrough, I will start looking at these questions.
Excellent. So you can see on the left, you have the virtual chamber that we are training on multiple machines, and we are able to upload different build plates. And on the right is part-specific information. The yellow dots you see here is the location specific that we are interested in, that's identified by the region of homogeneity and the user. And if you click on one of those locations, you're able to see the prediction as well as the measured information. And at the end, once we are done, we are able to export the data in multiple formats. One of them is a SQLite database that can be read with any SQL database. We're able to also export it for Material Center. That's part of MSC software. And we're able to export it also to a Granta database. And the information we're able to capture from the prediction side, as we shared earlier, we captured the change in the chemistry due to the build, the higher order statistics, and the texture. And from that's from the prediction. And from the measured side, we are able to also store the information with an interactive viewer for the defects. So this is when we get that from micro-CT. If any of you will try to view some of the micro-CT data, you can imagine how painful it can be. Now you can feed it into Icam software, able to view it, and you're able to show you some of the mechanical behavior as well, different phases evolution, and the texture, all within the same place. And I made it in 20 minutes. Back to you, Jennifer.
Well done, Eamonn, and I commend the boldness of a live demonstration in a virtual forum. Always a bit tricky. All right. Well, like my upvoting comment has really helped me sort these questions quite well. First question: how was the optimized heat treatment determined? Using an experimental test matrix, Icme, or both?
Actually, we developed an Icme for different materials, and this is it's $1 million funding from NavAir. Then we use that to guide the heat treatment. Then we validate it with experiments.
Great, thank you. The next question is: how was the Icme framework utilized to predict/control the formation of as-built porosity?
That's an excellent question. Knowing the machine behavior, and the question, one of the questions said, can we apply that to ES? So we train the tools on the machine, and the training process takes only 1 or 2 build plates. And once we train the Icam software on the machine itself, and we know the material, we have an ICAM database that takes into account microstructure evolution as a function of temperature, as well as the hierarchical simulation in interaction with SimuFact. From there, we predict location-specific distortion, which help us later on to design the build plate and design the orientation and predict the residual stresses in the as-built condition, and then later on after heat treatment, and if there is any need to consider during the machining operation.
Thank you, Eamonn. Okay. Were the microstructural textures analyzed in the bulk or near surface? Can the approach predict near outer surface, up skin, down skin, or is this only after heat treatment?
So that's a very loaded question, and because it has a lot of layers in it. So let's talk about the texture first. The texture prediction is related to the thermal profile, which is planned anywhere within the part. So if there is variability in the thermal profile in the part, then the texture prediction will yield that. The measurement itself for the blind testing was selected to be in the bulk of the material, and this is where we identified by the samples that was extracted that you saw in the earlier slides. As for predicting texture evolution on the subsurface material, that by itself is highly material dependent, and if we are using a net shape material, which is not in this case, but if we're using a net shape material, especially in the topology optimized part, we have another database that we upload to give you an indication what will be the ODF related it. And the texture here is the crystallographic texture. We are not talking about surface roughness in what sometimes is referred as surface texture.
All right. Thank you, Eamonn. Okay. Last question. But there is a lot in this Q&A, so should you want to answer those generally in the chat, feel free. But last question, what numerical method is used for microstructure prediction? How does the mesh of the thermal model translate to the mesh of the microstructural prediction?
So this is where it comes to the paper I shared with you with the crystal tracking. We developed the methodology independent of the FEM mesh of the at all. SimuFact implemented that very well. They use what is other tools use particle tracking, and in the particle tracking, you have a marker within the FEM that's able to average the information about it and export it. And once it's exported, now you have a material model that you don't need to make a mesh. What you have is a database of the thermal profile as a function of the location, and then you are calling it with the crystal tracking. And the crystal tracking is a volumetric information between 4 corners. And we demonstrated that using the deformation gradient for large plastic deformation in the paper that was published in 2017.
All right. Okay. Well, thank you so much, Eamonn. Appreciate it. And we'll move on to our next speaker.
Thank you. All
right. So next up is Justin. Hey, Justin. All right. Justin Gambone from GE Global Research will be talking to us about his efforts on Inconel 625 within the Quality Made program. So, Justin, over to you.
Excellent. Thank you. I'm going to share my screen and we'll jump right into this. Quick mic and screen check. Am I coming through?
Yes, you are.
Excellent. All right, thank you, everyone. So I'm Justin Gambone. I am from GE Research, so working in conjunction with GE Aviation, Additive and Power. We are the corporate division of GE, and I am the PI for the ONR Quality Made effort that GE leads, the Icme Informed Quality Program. So with this presentation, I'm going to be running through a few different technology areas. If I can get this to actually progress, there we are. And really looking at this, before I dive into the actual technology, I want to ground us in what we're trying to do for this program. For part qualification, part certification, there's a variety of developments and procedures in place that really allow the progress of qualification of a part to be elongated. So it can take some time to get through all of these steps. And I'm not going to go through all the details here. I think everyone on the line is aware of these challenges. Qualification, you have to complete your first print, so get past build crashes, go towards conforming geometry, but eventually towards more material-specific questions, low-rate production scalability. There's essentially a progression of qualification steps and procedures to really get a part to go into production. Similarly, for certification, when you're looking at scaling capabilities of additive manufacturing across more machines and across a full fleet of machines, you have to start looking at how things can change in the additive process and ensure that everything is staying consistent or within spec of what's allowable. So I'm going to be using this as the framework for today's discussion to really talk about how the quality made effort fits into these paradigms. Now let's talk part qualification first. So the impetus behind this quality made effort that GE is leading is really around taking insights and developments from process qualification. So when you're working with a new machine architecture, a new material in the machine, we have to go through a qualification procedure for that specific material and to really formulate all of the knowledge in a more representative manner that can then be further provided and leveraged as you go towards specific part qualification and part certification. So all of our material insights, sensors, controls, and simulation capabilities from process qualification, finding ways to pull more of that knowledge and insight towards part-specific areas so we can more quickly move through part qualification and leverage along that certification pipeline. By doing so, we're really looking to augment and accelerate every step along the way for a part qualification procedure. So here on the right side of my slide, I have the 5 toll gates that were shown previously. And with quality made, we have a variety of technologies that are meant to build on top of one another and allow ourselves to more quickly iterate or converge on solutions for each of these toll gates. And so just shown on this slide are a few tidbits of the technology areas where, for completing a first print, we have orientation optimization, taking into account overhanging regions of a part, support generation, recoder interactions to identify the best potential orientations of a part in the machine. For geometry, thermal simulations that allow us to understand the part distortion effects and compensate for them so we can get to CAD conformity more quickly in the part development process. Feature qualities leverage intelligent feed-forward control strategy. So we have more localized control of our additive process and when needed can adapt our process procedures to account for these variations that we see in the geometry. It's really inducing differences in melt pool behavior during the print process. Material quality leverages quite a bit the Icme-driven material prediction capabilities for Inconel 625 for us to understand the reliability and robustness of the end result material quality. And finally, when we go towards low rate production, we start leveraging one machine sensors. So we start looking at build-to-build consistency. So these are a variety of technologies that really impacts that qualification pipeline. I don't have time to go through them all today, but I am going to be going through a few examples of this, especially around the feature quality aspect. And then I'm going to go into the part certification aspect of the technology. And just as an end result for this, all of this is meant to really drive towards faster part qualification. So we have to do all of these steps. We have to hit every one of these types of toll gates with acceleration technologies to be able to really see a major reduction in part qualification time. So my example today that I want to run through that's really showing how we interconnect some of these technologies to accelerate and pull insights from process qualification to part qualification is really around intelligent feed forward and its convergence with simulation. So intelligent feed forward is a technology developed out of Lawrence Livermore National Lab, one of the members of our team, that really looks at doing localized process control of an additive part. And so the procedure that we take is we create a standardized build file, essentially an essential template for the part being generated across the 3D geometry, and we put that through an analysis. So we look at essentially feature extraction. So in this case, trying to identify where certain variations in that scan path really occur during the print process. And in this case, this example is really looking at regions where an overhang can occur. For essentially looking at a laser strike during the processing of this part, trying to identify where we start approaching that overhang region. And with segment 123 shown in the center of this slide, it's kind of the bulk region of the part. But then as the laser strike is going closer and closer to the edge of the part, towards that overhang section, we start identifying that it goes towards that very far edge, where essentially 128 is earmarked as the first layer above an overhang. 127 is the second layer above that overhang. Now, this type of demarcation of process variation along that laser strike then allows us to have more localized compensation and control to allow ourselves to have a more measured response to that change in process behavior. So taking that single laser strike that sees it going from a bulk region towards an overhang, we can now take that same laser strike, that same continuous movement of the laser, but now we can modulate the laser power or modulate the laser focus along that length, essentially create a gradient that steps us towards a more optimized scan strategy meant for an overhanging region of a part. And this allows us to have essentially no stops and starts, but it gives us a way to now have a smoother transition as we go between different features of parts and allows more tailored features as required for a part. Now, when we look at this type of technology, this type of control methodology on the machine, there's a lot of things we can look at here. 1D features, like what direction are the scan strikes going into? 2D features, so more of area-based understandings of wall thicknesses. Are we entering a corner of a part or not? And then 3D features, the level of an overhang, the height that you are into a part, how far away from the build plate are you? And for every laser strike, you could potentially have many different types of features that are associated to that one laser strike. You could have an overhang region that's also a corner. You can have a tall section of a part that's also a very thin wall. And so it's important for us to understand all these types of variations and use IFF to allow ourselves to accommodate changes where we find it's actually important. And to help accelerate this, we really started tying in simulation capabilities. And so for this example, we're taking intelligent feed forward capabilities for scan path control, and we're leveraging thermal simulations developed by ESI in association with Honeywell to look at strike-by-strike based material response of a geometry and see what the thermal response looks like for that part. And so for this example, we're actually looking at individual strikes being associated to it that are actually the IFF outputs to see how the thermal response changes, in this case, in regards to the overhang area, but also the length that you are into an overhang, and see what the thermal variation really can look like, and allows us to identify if this is a feature that matters and how much so, and how to go about controlling it. So we're able to pull thermal simulations to have optimized control during our process qualification stage. But now furthermore, we can leverage this in the part qualification procedure. So we now have tailored control strategies around critical feature sets that we know we need to control better in the additive process. And we want to now leverage those in part qualification. So IFF itself, Intelligent Feed Forward, is meant to take those same feature sets that were developed under process qualification, now apply them to new geometries, identify similar feature sets when we go to a new type of design. But furthermore, we're able to close that loop between the controls and that thermal simulation, and now run that same thermal simulation strike by strike on a new geometry, tailored geometry that we're looking to do process qualification on. It can provide assessments around thermal buildup of regions, show ourselves optimal orientations of the process and an understanding of the impact of our tailored control strategies. But then taking a step further for intelligent feed forward control and this level of insight into the scan path control of an additive system, we can then furthermore illustrate how scan paths are being applied to a new geometry, inform the qualifying body of where and how feature sets are being flagged and identified through advanced visualization capabilities. Taking ourselves a step beyond what's typically seen for additive technologies, where you look at essentially a layer of the scan path at a time, which is shown on the slide here along the right. But now also being able to overlay these same type of scan path controls with the CAD model. So you get a one-to-one view of where and how control strategies are being added or being used to mitigate new types of design features. And then a step beyond that, looking volumetric. So looking at the entire 3D body of a part geometry and then flagging or showing regions where certain types of feature sets are found or identified or leveraged or controlled using intelligent feed forward. And the same type of overlay of information, this CAD-oriented understanding of process space, is also the same metric as the thermal simulations as well. So that's one example of how we're trying to leverage things like advanced controls and simulation to provide faster insights into a new process, and also leveraging our process qualification towards new parts. But I also want to touch on certification. It's an important aspect of additive manufacturing that we really need to understand better and really need to push ourselves towards better characterizing as we look to scale additive manufacturing beyond just a few units. So while qualification is all around proving the capability of a new geometry to show consistent properties to what we expect from our process qualification, part certification is really around consistency. We know we have a good geometry, a good scan path, a good build process parameter, but now we have to make sure that as we scale from 1 machine to 50 machines, and those 50 machines from just a single build to years of operation, that we keep everything in check. And that means system level inputs, making sure our material feedstock is adequate. Our build process, ensuring that we have consistent build environments during the build process across that fleet of systems. And even post-processing, looking at powder removal or heat treatment and ensuring consistency in those regions. And it's important for us to understand the bounds of these, but also be informed of why those bounds exist, as when you scale additive manufacturing, things are going to vary. As you have different sites, different operators, and over a long period of time, things will change in the process, and we need to be ready to answer questions when we find those deviations actually occurring. So for the Quality Made program, we have leveraged the similar technologies that I was already showing in part qualification. Now we're leveraging the same things in part certification. We're using sensor-based systems developed by Penn State, coaxial multispectral sensor that looks down beam at the melt pool behavior. Similarly, Penn State is also looking at the build process from a gas flow environment, creating a new module that can go into the chamber so we can measure the gas flow across the build region in as unobtrusive as much as possible manner. And then also, an area I'm going to touch on next is Icme simulations. So we've leveraged Icme simulations in part qualification towards optimizing heat treats and understanding the resulting impact on our mechanical properties. But we were able to take those same simulations and really start driving towards insights around powder feedstock and heat treatment profiles, where when looking at this and diving a little bit more into this Icme-driven insights, we have a fairly complex Icme model that takes into account the initial chemistry variation of the part. It takes into account the different types of heat treatments we see during the build process or the post-process steps. And once we built that type of model, we immediately started asking questions around what if the compositional variation changes of the feedstock powder? Even if it's within spec, what if it's to the upper limit or the lower limit? What if it's out of spec? Then we also asked a question around process variation. What if a heat treatment's held a little too long or it's held at an incorrect temperature due to an issue with a thermocouple? What are those repercussions? Because in the end, when those happen during process scale up, that holds up parts, that holds up pipelines of production as you have to go through and answer these questions, or potentially just scrap parts that may actually be completely adequate. And so we're leveraging these Icme simulation to really exercise these inputs so we can understand the impact towards resulting material quality against them. So on the bottom of this chart, just showing two snippets around, first towards the left, the sensitivity process towards changes in the material feedstock. And on the right, essentially a curve generation that lets us see, based on temperature and time in excess or in reduction from the typical procedure, what's the impact towards the end result material quality. And then finally, last area I want to touch on towards the certification end is again towards the sensor-based aspect. I already touched on this, but during the print process, we want to ensure that the build chamber and our build process procedures are consistent print to print and across fleets of machines. And so we have integrated a sensor system into the additive process that allows us to look at narrowband spectrum of emissions of the melt pool itself, so we can understand where and how process variations occur. And then in addition to this, we've also developed with Penn State a calibration procedure for this. And actually that led to the gas flow sensor that was shown previously, a way for us to get a calibration module within the chamber unobtrusively so that we can get the right information to level set the sensor across a fleet of printers and also a printer over a long period of time. And what this provides us with now is a calibrated data set for each print that we can then understand the impact towards process variations and inform NDE experts around changes in that process and where and how they occur. So overall, just walking through a few examples of this Icme informed quality program that we have in conjunction with the Navy, where our next steps are really pushing towards transitioning this technology to Lakehurst site with a concept laser M2 system, integrating the sensor work and all the different software and simulation capabilities. Now, at its heart, this program is a technology framework that combines advanced simulations, controls, and advanced sensors so that we can understand and better predict the build process, but also by aligning all those bits of information, we're able to start really leveraging the additional understanding that each provides so we get higher confidence in a new part geometry as we go through part qualification, and can refer back to that same type of insight as we go towards part certification. And on towards the right slide again, just reiterating a thing shown on the previous slide, but really what we're trying to do is take these levels of insights that we have with a new machine or a new material, catalog them correctly, understand them appropriately so that we can further leverage them as much as possible towards the qualification certification pipeline. And with that, I think we have some time for questions. Happy to answer anything that may come up.
All right. Okay. So for folks on the platform, please pop your questions in the Q&A. If lots of questions come in, just upvote the ones you really want. But we'll start off with the very first question, which is, does the IFF approach account for variation in gas flows driven by build layout and product orientation, nearest neighbor proximity, etc.?
It's an excellent question. So when we look at within a single part, we can account for directionality of the scan strikes within that part. IFF does not necessarily extend itself to understand additional parts on the build plate. So if you have various ones across the build area, it does not necessarily account for that in the active control of that aspect. However, during the additive process and in the machine itself, when we're generating the scan paths and setting which parts are being processed, that is accounted for so that you work from downstream to upstream, so that you process certain parts before others to mitigate plume formation interference that may occur in an additive process. Furthermore, we have heavily been looking at the influence of plume interference and gas flow capabilities in the systems on the program, which led to one of the sensors that Penn State has integrated for the M2, so that we can understand what changes in gas flow can really mean towards both plume generation, but also interference and melt pool behavior in the additive process and the resulting quality that we may see. And we found that we're able to get it pretty reliable within the system itself and across the whole build area.
Thank you, Justin. And then another question within the Q&A is, has your V&V of Icme certification approach that you've described involved extensive evaluation of type 1 and 2 errors? Can you talk more about that and opportunities for further development?
So I'm not quite sure I understand the question in its totality. So this might require a follow-on, Brandon, to dive a bit deeper into this area. Our certification, so our Icme certification, we have looked at quite extensively in terms of both the end result material mechanical properties, but also material quality through the heat treatment cycles for Inconel 625, and have vetted the types of variations both in chemistry, segregation, grain size, to really understand the impact of heat treatment and the as-built structure of the part towards end result material quality. So it's an area that's active. We have done quite a bit to really investigate and understand the impact towards Inconel 625 behavior. But there's more that we're starting to find that can be further developed and leveraged to continue pulling on Icme simulations in new ways with this process, as I was kind of showing in the presentation at the end, toward more certification output. So certainly many opportunities, many areas for us to leverage this Icme type of simulation, but also certainly more areas for us to explore this as we tailor this Icme simulation towards other materials outside of Inconel.
Okay. And then the question from Sean is the Icme approach used to evaluate variations in chemistry and heat treatment cycle translatable to directed energy deposition applications? And I think that's you were kind of delving into that one a little bit, but I wanted to read the question out loud.
Yeah, absolutely. So I believe wholeheartedly, yes. The additive technologies are very similar across DMLM and DED, even electron beam, in terms of starting state of material of an as-built microstructure, then through the different heat treatments in the process. I see that this can very well be leveraged as we look towards DED applications or other types of metal-based additive technologies. And it really is towards the same system, just different starting conditions in how we initialize the material during the print process.
Thanks, Justin. And one more question. How does IFF compare with what is being known as support-free part builds?
Yes, so support-free part builds is really just going towards more extreme overhang conditions that you can generate without having to add on sacrificial material after the build is done. For those, just to level set what that actually means for the group. So 0-degree overhangs without having to have anything underneath that you typically would add in, like lattice structures. So IFF is really approaching that same type of development. So it allows us to push into those more extreme conditions, so we don't need supports, but we can also then further optimize towards surface roughness metrics or things like near surface porosity or other key attributes. So it allows for fine control. The idea behind IFF is that we can now take a geometry, parse it into smaller feature sets, and where we find we need to allow adaptive control. I don't like to add any additional control mechanisms if they're not actually required. But let's say you go towards these more extreme overhang conditions, certainly that's where we find that we need to change the processing conditions so that we can more accommodate the thermal buildup in those regions without supports in their process. And the key towards some of this is also trying to find ways to balance this type of support-free capabilities of additive systems, in addition to understanding the build rate implications as you kind of lower your energy delivery times or levels in those regions of a part.
All right. Okay. So one last question, which is for reviewing the output from the multispectral sensing, how difficult is it to upskill a non-additive TA or engineering technician to review the data from the build process?
Okay, so here we're asking, how taking this type of data and how do we actually approach that to different levels of technical expertise? I think that's what the question is really getting at.
I think so. I think it's really looking at how do we address maybe some more of the training for the workforce for upskills on interpretation of sensors.
This has been an extensive area of discussion that we've had with Penn State and with the Navy and Lakehurst around how we summarize this data, how we present it, and who are the users or the user stories around this data set. And certainly, some of this can absolutely be distilled towards somebody that's not as much of an expert on the additive process or around the physics of the process or the sensors. But really what it comes down to is having to succinctly summarize certain levels of information. So for an engineering technician that is running, not just that it's a need to be distilled so that a person operating 50 machines or 30 machines walking up and down the line can quickly see what's happening in the process. And so for this case, we find that simple summations of information for a layer, or showing how an overall metric is reading for across a build. So a quality criteria on a layer basis is a good way to kind of illustrate that, hey, something's going wrong here, everything looks good. And then we have further levels of insight for this data where, a quality engineer might want to see everything and pull it in, overlay it with eventual CT scans or overlay with the CAD to understand where and how this change in process is behaving. And so we've broken this type of sensor level insight into some of these different levels of process understanding. Quick summations at the machine, more detailed data sets that can be referenced down the line by a user expert to really dig into the data.
Yeah, it's really interesting. Like, and that's something maybe we'll touch upon a little bit more, right? Is the use of this information as part of a decision tool, right? And how do we kind of feed this information in various points, right? Like, so you talked a little bit about your interaction specifically with Lakehurst and what different users might view, right? Can you talk to us a little bit more about how they maybe interconnect with respect to what some of those envisioned workflows may look like, to use this as a decision tool? Because I think one of the important pieces is the information coming out. It gives us information to do stuff with. So what is it that we need to do? Can you speak to that a little bit?
Absolutely. So again, when we're in these discussions with Lakehurst and with a variety of Navy focals, we started off with just looking at what do we need at the machine. We need to understand, is something going wrong or not, so we know to stop a build or let something advance. So just understanding changes in the overall process behavior. But then we started pulling on different technical focals. And like one example was pulled on the NDE group, the non-destructive evaluation group at their site. And their first comment was like, they see T-parts and they look at things in quite a bit of depth. So their first request was like, can you get this data to us in a DICOM format so that we can put in the exact same tool that we currently use for CT? And absolutely. So that's something that Penn State's added the capability to do. They're already working towards that area. And that allows us to really start merging together these types of new of tools and data sets. And in this example, now we can start having CT data directly correlated to our sensor data, which is also in the same coordinate space as our scan path files that are text readable. So all of a sudden, the NDE experts are going to have pre-processed information around what we want to do from a control aspect, the sensor data from what happened in the printer itself, and then CT information of what the end result part looked like. And that is a very powerful type of data overlay that generates all new types of discoveries as you start scaling additive. And months down the line, as you start accumulating all this information, we'll learn and learn as time goes on and get smarter as a group overall.
Yeah, no, and that's great, right? Data is king. Data fusion, and how do we retrieve that data and get data into maybe known formats for other folks, I think is an important part of the conversation. So I'm glad you brought that up specifically about reading in data in different format. I think that's really great. So thank you so much, Justin. Don't worry, don't go too far. There's like a panel after this. So let me call up Glenn. Glenn, if you don't mind turning on your video and your mic. I saw you there briefly. Oh, and you're back. Great. Glenn, the floor is all yours.
Yep, here I am. Thank you, Jennifer. Let me see if I can get my screen arranged quickly. There we go. So the project that you'll hear about here is yet another one of Jennifer's Office of Naval Research quality made projects. This one has to do with the robotic laser additive manufacturing system. Again, same sort of theme that you've heard in the past two presentations. That is basically trying to ensure quality assurance in the part build itself. So I'd like to obviously acknowledge Jennifer for not just this opportunity, but her leadership in making certain that this program has been successful. I also need to acknowledge the Lockheed Martin principal investigator. I don't know how many of you know Ed Pearson, but he's done a really fantastic job on this project, leading the technical aspects of what you're about to see here. This is a pretty broad team. Lockheed Martin is the prime contractor on this, but you can see all of the folks who are on this team as well. So we've got a system that was provided by Lincoln Electric and resides at the Oak Ridge National Laboratories. So that's the system that you will see me talk about, and you'll see pictured here in this presentation. Lincoln Electric has provided technicians as well as engineering support to operate that system and to see the enhancements that we've made onto that system. While the Oak Ridge guys have done similar, right? You'll see a good bit of work that they've done with both sensor implementations and data acquisition. We've been supported by the America Makes guys, who are sponsoring this game day as well, with dissemination of information and such. We've got two prominent university collaborators as well. Carnegie Mellon University, Tony Rowlett, who was referred to earlier in one of these reviews, is working with us on the material characterizations. Jack Buth at Carnegie Mellon, he and his team have been working with us on some of the thermodynamic modeling that you'll see. And then Pete Collins, who was also gave a quick public service announcement earlier today out at Iowa State University. He's been on our team to help us understand some of the relationships from material state to being able to predict mechanical properties. So that's the team that we've had on this project for a while. This project, by the way, we are in our fourth year. We've got 6 months left to this project. In June of this year is the end of our period of performance. And so you'll see a good bit of work that you may have seen before, but I just want to kind of get everybody up to speed real quickly. Without hoping not to insult anyone's intelligence, just a quick what the laser hot wire DED process is. So obviously the process itself uses a laser for the main source of energy into the material that's being deposited. The main control parameters, process control parameters that we have access to are the laser power itself, the travel speed, how fast you're putting the bead down. This is a hot wire system, so the wire is preheated before it goes into the melt pool. So we can control the amount of preheat on that wire, and obviously we can also control the feed rate, how fast we're introducing the wire into the pool. The other factors are the preheat temperature. In some cases, we have preheated our build plate before beginning the deposition, and also the geometry of the part obviously is a factor in the overall process. What exactly the geometric dimensions of the part and the some geometric features of that part will affect the quality of the build and your ability to control the quality of that build. So the schematic on the right just kind of shows again schematically what we're doing there. And the system, unfortunately, it's hard to get good photographs of this system. We are building solely with Ti 6.4. So we've been using Ti 6.4 wire, and what it requires is a inert environment. We obtain that inert environment using literally a tent, if you will, to purge the environment while we're conducting the build. The reason we do this is because of the specific system that we use, namely the system that you see here, this robotic system, and I'll get into a bit more details on that in a moment. What our program is about, our final deliveries are a framework for developing this quality assurance, as well as a system itself. So to the left is a diagram that somewhat shows the interactions that are required, what I would call the data streams, right? The flow chart in some vernacular of the various functions that have to occur from the start of a design, a part design, all the way through to the build of that part and the inspection of that part. And so it's not intended for you to be able to read that chart. It's quite difficult to actually read it at the scale it is. The point is simply that if you go down the left-hand side of that chart, you'll see kind of what a flow is from one function down the next, and not truly a sequential, but nearly a sequential flow. But then as you come back up the right-hand side, you see that there's a lot of interactions between the data that are collected, and the data that are generated or synthesized through models and simulations. So for instance, the process mapping window that you'll see in a moment, which is essentially how we define our optimized parameters, or our parameters that give us the best conditions. That all ends up being determined initially by some models and sims, but the actual data that we collect from the in-situ process monitoring goes back to feed that process mapping, as well as to feed the thermomechanical models and the material state models to be able to validate those and improve those with the experimental data that we collect as we continue with this project and the builds. And so not only that experimental data, but subsequently the material state data assessment that Tony Rollett and his group are doing, as well as the mechanical properties data, all flow back into updating and making more accurate each of those models and simulations. The system that you see up in the graphic is the robotic system at Oak Ridge National Labs. One of our deliveries is a duplicate system to that will be delivered to the Naval Surface Warfare Center in Carteret. The thing you'll see in a moment, that system is not necessarily just a COTS type system that Lincoln Electric would deliver to anyone who's interested in buying one, but it also includes a significant amount of sensor and data acquisition equipment that's been added to allow us to be able to do the in-situ process monitoring and gather those data again that are used over in the framework to the left to validate and update those models. The other part of our delivery to the Navy is to demonstrate relevant Navy parts with this build and with the framework we've developed. What you see is a boss geometry. It truly is a big chunk of titanium, but the Navy had relevant interest in how well we could control the process while laying such a massive amount of titanium with this process. The other item up here, you see a graphic of it. It actually has been completed. It's an annular ring that we built, again, as another demonstration part for the Navy. The important part of this ring, or the significance part of this, is that this ring varies in thickness as you go up the height of the ring. It also varies in the ID and OD via overhangs that go from both an overhang towards the interior of the ring and then finishes off with an overhang towards the OD of the ring. So a rather complex design that we have also completed for the Navy. The last item that you see is this impeller design, and we are in the process of completing that demonstration. It just started off last week, as a matter of fact. The system that we have, again, is a laser hot wire directed energy deposition system, And this is a schematic of this system. As I mentioned earlier, it's really difficult to get good photographs and capture the essence of what's here. It's better done with the schematic. What you see here is, first off, there's an environmental enclosure. Again, this is a laser system, so safety reasons, you have to have a light type laser enclosure around the entire system. But there's also, you see in here, shaded in a lighter color, is this argon management system. So we purge the system with argon. We've got a flexible tint to allow that environment and to maintain that environment while the robot motion is employed during the build. This is we felt like this was a much more relevant or a much more much easier way to do this than to try to do a fixed or a closed volume. There's the motion system is an ABB robot. You can see that it's a 6-axis robot. We've also got engaged in here is a 2-axis positioner. So the bed that the part lays on, this positioner can actually rotate and turn that part with a turntable. The process equipment is a laser line 8 kW diode laser. We've got Precitech optics on that laser, and it's again got the Lincoln hot wire system that delivers the wire. So that's kind of the standard system that you would see for a laser system. What we've added to that is that we've added 2 IR cameras, a near field and a far field, a FLIR A70 and an A700. The near field obviously is on the melt pool. The far field is trying to get a larger picture. It's actually mounted on the positioner and trying to get a larger picture of the overall field of the thermal field for the part that's being built. In addition to that, we've added 2 Prosilica vision cameras. One is mounted inline with the travel direction of the robot itself, and the other is an oblique camera that's kind of off to the side. Both are grabbing images of the melt pool itself. Finally, we've got 3 different pyrometers. One is a melt pool pyrometer that is, again, measuring the thermal conditions at the melt pool. And then we've got leading and trailing pyrometers just ahead of and behind that melt pool as it travels. And then we've also implemented a profilometer, a keyed profilometer, so that we can scan the part intermittently during the build. So we'll stop the build at designated layers and scan the part to again provide data back to our models of things such as bead height. We will predict bead height at a specific layer, but then by measuring with the profilometer, we can determine the accuracy of that prediction during the actual build. Essentially, what we've done is we've had a fairly determined build progression. So when we initially started this project, we laid down simply bead on plate. We didn't even try to build upon the laid down beads, just to try to get a better understanding of the process control itself, and what the process windows look like. What our schedule parameters. I mentioned those 4 different control parameters. What those parameters look like and what they produce within a given boundary. So we use that to get a reasonable approximation of what a good set of schedule parameters would be. We progressed on to doing stacked walls, is what we called it. Basically, just one bead on top of another. There's not 2 beads aligned here. It literally is just a vertically stacked wall. And then we went on to build large blocks builds that are multiple beads across. So you can see there's multiple beads going across here, and then multiple beads stacked up. We went on to build a more complex geometry. Unfortunately, this is not as the best view of this, but essentially, this is a large wall build with another perturbation wall that's a single bead layer going up, and is actually angled down as it goes out. So we ended up, we progressed to that more complex geometry. In each of these cases, we used specimens from these builds to determine material state, and we did some mechanical properties testing to correlate that material state to the mechanical properties. we got into, as I mentioned, we did this annular, what we call an annular ring. What we did before that ring was we took and just extruded that cross section and built a straight angled wall out of that cross section, and then had that machine to show that we could actually, we had built that properly to where the part could be extracted or machined from the build that we had conducted. One of the first things we did, I mentioned process maps. So what we learned in our initially, what Jack Buth and his team learned was that we needed a process window within which we could have a reliable deposition and something that would deliver a good quality deposition in each different bead that was laid. So it's important to deliver the right amount of energy into the melt pool. So what you see here is that Jack Buth and his team have defined what they call a remelt ratio. And so basically, depending on the process parameters, how much energy you're dumping into the material, as well as how quickly you're feeding material into the melt pool, you will remelt some of the material in the substrate or either the previous builds, and then you'll add some melted material. And Jack's come up with a formulation for remelt ratio. And then what he did is he developed these process maps. And the essential part of these process maps, and they are color coded, and you might guess the red section is a place where you actually don't want to be, and the highlighted green sections are really kind of what I'd call the sweet spot. So what we've been able to do is, through a variety of experiments, a DOE, if you will, on the more relevant process parameters, the total power, the velocity, which is the speed, travel speed, and the wire feed rate. What Jack's team would do is they'd define a desired remelt ratio, and we'd go in and conduct these builds such that we could build maps that showed for a given hot wire power, what was the total power, which is a combination of both the laser power and the hot wire, that would give us a good build. And what these contours are meant to define is there are regions outside of this green highlighted area where you will either get a keyholing effect, that you're dumping too much energy into the part, or you'll get a dripping boundary. So for a given hot wire power along one of these contours, if you get below that contour in this range, what will happen is you'll start dripping wire into the melt pool, and you'll end up with an unstable build. And so there's some significance to that you'll see further on in the presentation. So keep that in mind when it comes to that. But again, the essence of these process maps is to help us define what a good set of processing parameters is across that entire build profile. The overall model, or the overall workflow through this framework, starts really with the thermomechanical modeling. So as I mentioned, Jack was able to define these process maps that help give us a better idea of what the optimal processes is. But then for a specific geometry, we'd also go in and conduct thermomechanical models via either finite element analyses or through analytical, I'd say simple analytical models of the geometry that would allow us to understand essentially what the thermal history is throughout the build of this product. And so the essence of doing that is, in order to understand the thermal history, once you have that, now that all feeds back into the models that Tony Rollett's group uses to do the material state, to understand what the morphology is within the specific areas within that part. The thing about the thermomechanical modeling is that it also helps us to understand a reasonable scan strategy for a part, or an optimal scan strategy for a part. So these thermomechanical models would help us to predict both distortions and residual stresses, as well as feeding that thermal history into the material state models. So when we were able to, as a use of this thermomechanical model, we could go in and do different scan strategies for our parts and get an idea of which of those scan strategies would help us to minimize residual stresses and distortions, as well as to maintain a stable process during the build. So the next step in our workflow is to take that thermal history, and this is where Tony Rollett's group would come in and use that thermal history to understand what the material state is for that particular build. And so this microstructural predictions would take into account, again, that the detailed thermal history within each cycle for the TI-64, for both mainly for the influence on the previously laid beads. And so there is the subsequent heating is really important to understanding that morphology. And one of the really relevant discoveries that Tony and his group made, it's difficult to see in this particular stacked bead, but if you look closely, there are these white bands that are evident across this sample. And initially, I certainly defaulted to thinking those white bands were relevant or tied to the bead geometry, each layer as we went up. That's not true, though. The bead layers can be seen in the geometry of the part itself. So these white bands were actually a byproduct of the thermal history. And it had to do with the amount of reheating and how close we were to the transit temperature. Tony can give you a much better explanation of that if you're interested in hearing that. The point is that these models were able to, with his models, he was able to predict the occurrence of these small banding regions throughout the build of the layers. And again, based on the thermal history that each layer saw as the build was progressing. The last part of the workflow with as far as the models and simulations go is the acquisition of or the transition from the microstructural or the material state to the mechanical properties. And this is where Pete Collins' group comes in. So he's been able to use a model that I know he's used on several different processes for TI-64. And he's been able to apply that model to predict both the yield strength as well as the ultimate strength of the builds that we are conducting. There's several different things that come into the model itself. Actually, the composition is one of the primary things that determines that strength, as you might imagine. But then secondarily, the microstructure, what the phases, the different phases are, as well as the grain morphology within the material state, all come into play in defining the yield stress and the ultimate tensile strength. Another significant thing that Pete was able to show was that the texture can change the strength values by as much as 10 to 15%, and then strain hardening as well is a major influence on what the resulting yield strengths and ultimate tensile strengths are. We were able to, another significant thing that we were able to do, I mentioned earlier that Jack Bue's team has produced these process maps, and that they were able to predict the dripping boundaries based on contours of the hot wire power and the total power versus the travel speed. We were able to, with our image cameras, we were able to capture the melt pool image and to process the melt pool characteristics of width, total area, and length of that melt pool surface area, and able to do that in real time. What you see in this image is this is the actual melt pool. This is a reflection that's not part of our overall calculations. And so we were able to process this real time, and this allowed us to be able to close the loop on the control system itself, so that now by specifying a set melt pool area and a targeted laser power condition, we could then control the laser power to maintain this melt pool area. But significantly as well was the data that we took and post-processed those data. And what we're able to do, Jack's team again was looking at a neural network, long short-term memory, recurrent neural network, and they were able to post-process those data. And the relevance of that is that when they were able to do that, they came up with what they called a regularity score from this neural network. And by looking at a stable bead versus an unstable bead, if you pay attention only to the straight, steady line up here, these others are transient at start and stop. The stable bead gave a very uniform regularity. We purposely induced an unstable bead. And when we did so, you can see that this neural network would predict that instability. That instability was literally moving into the dripping zone. That's how we generated that instability. The relevance here is that we're able to take the in-situ process monitoring data, particularly in this case, the image data, and we're able to produce from that or predict from that when our process is headed to an instability. We're working now, Jack's team has been working, unfortunately I was not able to get those results in here, but they've been working with the IR data as well, and are getting similar results with the IR data that is able, again, those data are able to predict through the neural network when that instability is about to occur. So the real essence and the holy grail for us would be to be able to implement this sort of algorithm or something close to it that could do that real time. So that as we got to an instability generated by either the geometry of the part or a miscalculation on the thermal, the predicted thermomechanical properties, we could then control our process to make sure that we did not actually induce that instability. I mentioned earlier the Navy demo builds. This first one that we did was again the Navy was interested in a fixed section build, so we did a single build on a round plate. It was about 45 minutes per layer that was built without interruption, and the whole build was about a 40-hour build. So again, it was incremental. It was not a continuous build. We would stop at various layers and pick up the next day or the next morning, etc. The image that you see right here is when we'd gotten up to layer 25, and the final image is, you can see it's 53 layers at 18 beads per layer. The essence here was being able to not only control the process, but predict what the thermal conditions would be as we conducted that build. The bottom line is that we are delivering this framework to the Navy. So this is the system, the Navy system. It is currently being built at Fort Collins. We have again that plan for delivery to the Naval Surface Warfare Center in Carter Rock in the June timeframe. Lincoln Electric is conducting that build up at Fort Collins. Right now at what was previously a Wolf facility. We are going to demonstrate this impeller build actually at that system, on that system in Fort Collins before it is delivered to the Navy. And that'll be part of the checkout for that system. We have been able to develop this entire framework and demonstrate this entire framework. Again, that is the connection and the interfaces between each of the different models and simulation that we're conducting, as well as the experimental data and in-situ process data that we've collected. We've been able to develop a closed loop control system that we've implemented at Oak Ridge National Laboratories. I'd really like the opportunity to continue advancing that system to be more of a multivariate control system. I've heard mention already of AI systems and ML systems for control. I think this particular process is extremely suitable or suited to that. The time constants are much slower than what they are in the laser powder bed fusion process. So I'd like to continue maturing that to be able to develop that control system as a multivariant. I mentioned that we did this BOSS system. We completed the Annular Ring, as you see here, and are in preparation to deliver that to a Navy program for them to get the final machine part out of this, with some plans to use that as some sort of a test article, potentially a qualification type test article, or within an overall vehicle system article. And we are in the process right now of building this Navy impeller. It will be built both at Oak Ridge and at Fort Collins, as well as our final checkout on the Navy system when we deliver it to the Naval Surface Warfare Center at Carteret. So that's kind of the rundown. If you've got anybody's posted any questions, I'll be glad to address those.
Oh, Glenn, you have lots of questions. So here I'll start it off. What I'll say, by the way, folks, in the Q&A, upvote some of those questions while I share this very quick anecdote, which is unique to the LM team. So we have, some big Navy conferences, and they always ask me to bring, demonstration stuff, right? And someone said, oh, well, what about some of the things coming from Quality Made, and what about the big metal stuff? I was like, guys, I can't carry that. Like, I have no idea how to get that there. It's a couple 100 pounds. So I thought you would find that funny, Glenn.
Yeah, we've run across the same issue exactly. These parts are not the sort of thing you go put on someone's desk.
Yeah, right. No, so don't worry. That went away very quickly when I was like, that's like a couple 100 pounds, and have you seen me? Like, this is not going to work out well. Okay, so hopefully gave enough of a chance for people to upvote some questions here. First one is, how many iterations of modeling and simulation tool refinement were conducted using sensor and measured data? Are there lessons on how to reduce the number of iterations?
Yeah, so I'm not going to be able to tell you the exact number of iterations we've gone through. What I can tell you is that we continue, right? So every time we do a build, we take those data from the in-situ process measurement. We provide those data to the guys at CMU, and then they're using those data to validate their models. I can tell you that I think Pete Collins has probably iterated his model enough to where it's about as accurate as it'll get. I think during our program, he added one more parameter to what he was doing, and bumped his accuracy by a couple of percentage points. And when I say his accuracy, what I mean is his ability to predict what mechanical properties are going to result from a specific material state. But we have continued to iterate. Every time we do a build, we use those data to iterate on the models. It's a bit difficult to answer that question because of the fact that part geometry plays a pretty big part in exactly how accurate those models are. So we're continuing that right now. Unfortunately, I can't tell you exactly how many iterations we've been through. Jack or Tony might be able to answer that better for you.
Yeah, and what I'll also maybe add on to that is the fact that the Icme piece of that has been pretty seamless and moving back and forth between analysis and iterations, right? So you might have a lot more iterations computationally than on the build as you hone it in a little bit more. Okay, next question. Did you find that the profilometry technique was able to sufficiently capture the temporal evolution of the as-built, oh no, where did that go? As-built geometry and any distortion? Were those measurements compared with model results?
So the profilometry technique is we've been using mainly to understand our height, our part height. So one of the things that Jack Bue's team predicts is the bead height. And they've done two different bead height calculations for us. One is the very first bead that you produce, because that one's on the build plate surface itself. And then subsequent to that, trying to predict what the build height is based on our process parameters. And so what we use the profilometer for is to go back and measure that build height. So we'll measure it on our first bead, the first layer that we lay onto the build substrate, and then we'll go back and do incremental measurements. The last one time we did it was every 5 layers. And so what we're doing is trying to feed that back into Jack's model so that he can update his model for that. We're not using the profilometer to try to understand distortions during the build. The way I see it, I'd love to be able to do that, to be able to correct the build on the fly. That's another maturity and progression. What we're doing for understanding the overall build is really post-build is doing ferro arm scans and CT scans of the part itself to get those dimensional results, as well as with the CT scans to try to get some volumetric results and understand any porosity that we might have.
So speaking of CT scans, that's a nice lead into the next question. And the question is, have the parts to date been CT scanned for path planning defects?
So yeah, I don't know about path planning defects, but they have definitely been CT scanned for both surface and volumetric defects. I don't know that I'd classify that as a path planning defect, but yeah, we definitely have seen places where we have underbuilt parts to where if you go to machine this part, you may not get the part you want. And we've also been able to scan, again, CT scans just for the ability to understand what our distortion is once we have generated that part. So, and again, both CT scans and a ferro arm scan for those dimensional aspects.
Great. So I'm going to ask you one more question, but I'm going to leave these questions in the Q&A for the panel. And the last question I'm going to ask for you today, Glenn, as you're in this hot seat, is: do you foresee this system or systems like it being useful for repair of serialized components? Any needs for standards for digital twin formats for part quality info to support that workflow?
Ooh, that sounds like a lead-in question. Yeah, so this could definitely be used for repair of serialized parts. I think that you'd need you need to add some front end onto the workflow. I've actually thought about this, because if you were going to go back in and do a specific part, right, and try to repair it, like you've seen, well, you may have seen if you attended earlier this week, the cold spray technique has been used for that. I think for this technique, though, you would want to go in and create a model of that part first, create a 3D model of that part initially, because one of the first things that we do is with the LEA product, at least, it's called Sculpt Print, but it's a path planning module is what it is. So you'd have to do that initially to be able to go back in and repair those parts. I don't see any reason why that could not be done. The idea of having the digital twin, again, is depending on the part itself, you may be able to avoid that pre-scan if you've got enough confidence in your digital twin that part is going to be reflected by that digital twin. That could easily make that process of repairing the part more efficient.
All right. Thanks, Glenn. So I'm going to hand this all back over to Brandon to herd us through the next portion of the event.
Thanks, Jen. So at this point, I want to welcome Justin back up to the stage. I'm hoping
Glenn, don't go away. You need to stay.
I didn't go away.
and Eamonn, please come up and join us on the stage. So we would love for folks to continue to kind of provide some Q&A. I have some questions, of course, but really this is an opportunity to kind of extrapolate on everyone's perspective, right? We've heard the great work that's happened here. We've made tremendous progress, and as I was thinking late last night and alluded to when we started this morning or this afternoon, we've come a long way in the last 5 years, to say the least. I think back 5 years ago, and I think a lot of what we hoped for and we wished for at that time, we just heard a lot of what we were all hoping to learn. And so very exciting. So that's my perspective. What I'm curious of, though, the rest of the panelists, how has your perception of Icme, advanced data analytics, process monitoring, or model-based approaches changed as a result of this?
So why don't I start off, right? Because to be honest with you, like 5 years ago, either I got the responses of this is exactly what we need, or you're crazy. Like those were those were the two common responses, right? And I think that it's been really impactful over the last 5 years to show where we apply different parts of this knowledge. I think that there's been a lot of hesitancy given our more traditional qualification certification pathways, and it takes time to build trust. And I think that there is a lot more trust now, and our ability to really show where we can impact more distinctly by informing different parts of the process, informing qualification, and give information that they now realize that there is no other way to get it except through our computational tools. And so it's taken time to build trust. It hasn't been easy. And so I'm very proud of this team and how far they have come over the last 5 years, especially given a pandemic. So there have been a lot of really big hurdles, to say the least. But I'll hand it over to the rest of the team to perhaps give their perspectives.
Yeah, so I go next. In terms of kind of how this has shaped my process around additive manufacturing, I mean, it's and how it's shaping the industry is pretty profound. I mean, there's always been developments around sensors, controls, simulations, Icme simulations, thermal simulations. These have been happening partially across the industry, but to try to shepherd them together is a whole journey, just to see where do you find a good alignment between these technologies or not? Where do they help add on to each other? And it's kind of provides new types of understanding of the process, how these things come together, how the physics of the process is actually influenced by all these extra variations or optimizations. And so it's illustrative, and it's really guiding these technologies on how to better interact with one another moving forward as well. So I'd say that's a major area for development. And I'm seeing that this has become more critical over time, because I think over this past 5 years, additive has started being used more and more. And there's a big difference between when you're trying to get one part through qualification, where you can kind of move it along at a pace, versus trying to get dozens of parts through qualification. This technology need is driven to a higher and higher degree of requirement to really keep up with the planned demand and ramp of the aerospace industry in general.
Yeah, I think that's an interesting perspective that I don't know if folks would have said. I don't believe I can take additive to serial production unless I have some modeling or measurement techniques under my belt that we just heard about over the last hour and a half, right? And I think again and again, as we've heard multiple times so far today, there is a lot of value here. A lot of value in this space to aid us in our qualification journey. I don't know, did anyone else have anything to add? I really like the way you put that, Justin.
Yeah, so Brendan, I need to quote one of my colleagues, a guy by the name of Nermal Iyengar out in Sunnyvale. He made a statement one time that I thought was pretty neat. He said that we have paid dearly for several decades now for homogeneity, and what he meant by that rang true to me, right? So in my career with NASA, right, when we got a thick plate of aluminum, we knew exactly what the mechanical properties were in that plate in any direction, at any thickness, or any location in that plate. And we knew it because of the amount of effort that had gone into specifying the process by which that plate would be made. But with additive manufacturing, you're kind of making the material while you're making the part. And so I think that if any process that's out there today is really ripe for an ICM approach and a modeling and simulation approach, and well, I hate to say it, but a verification by simulation or by modeling and analysis. Then additive manufacturing is it. And I think it might be the technology that finally drives us to being able to bring those kind of analyses and computations into the TDPs and into the qualification that's needed. I don't know if people were ready to accept that just yet, but I think that AM is probably going to be the driving process that allows that to happen.
And echoing Glenn comment, and I'm sitting down listening because this effort and where we are going is dependent on the leadership from ONR and the rest of the team from Lockheed Martin and GE and the individual team members within our group, where enabling model-based sensor-assisted qualification wouldn't happen if it's not coming from the top down. And knowing that we can able to give this information on 3 drastically different systems to the decision makers, that to convince them that it is possible to take some model-based information and sensors information on 3 different activities with 3 big teams like that, I think it's a win for everybody, all the team contributions. And that activity by the summer, having it in one place that can validate it, total blind validation, I think that will be the ultimate test is later on when it's all run by the Navy to come back and say this is working and this is not working. So I don't think that will end by the summer. I think that's another 2 to 3 years to see the ultimate results of this, where now we have actual users who are totally hands off with what we have developed. So I'm pretty excited of just being with the team, sitting here with the leadership from the Navy. So thank you.
You're welcome. No, and I think that point takes me to the next question I know I had. Folks joining us, please feel free, add your questions in the Q&A. We'd love to get them and discuss them. But, really, Eamonn, you hit on it. Where do we go from here, right? I mean, we've come a long way. And I'd be interested to hear Justin and Glenn's thoughts. Of course, Jen, I mean, anyone. I won't call on you. I won't pick on you to put you on the spot. In my mind, I heard a lot about control today, control frameworks, different protocols, digitally enabled quality management, but what do we got to do to really fully realize that? Where do we go from here? You're on mute, sir.
I'm mute, Justin.
All right. So I would say what comes next is really around what I see as scaling and data. So we've got an understanding now of the different simulation, Icme simulations, different types of physics simulations, sensors, control strategies, all of that's come together. We are understanding how to tabulate that, how to catalog that, how to track it all and intermix it as well. And this is essentially what the handoff is with the Navy between all of these projects. We're giving this capability, we're giving this traceability of the process. But what comes next is scale. Having this printer running for a year, collecting this type of information, we're going to have data sets that we've never had available before. And leveraging that to become even smarter, to understand things that we maybe never even considered is going to be kind of the next step of this. But what that requires is kind of a strong foundation of just having consistent capability and consistent data management, data integration, not just in the machine and what we're handing off, but also into the greater structure that we're going into with the Navy of any type of post-processing or pre-processing of data files or CT scans that go in addition to these additive systems that we're handing off. So tying that together, tracing it, keeping that traceability, building out that understanding, we're going to be smarter as the years go on with this as kind of a bedrock foundational step towards it.
And if I may add to Justin's comment, I think the next steps, in addition to what he mentioned, is interoperability within the Navy itself. So now we have 3 systems sitting in one place. Will it reach to a level where the Navy team will be able to talk to all 3 machines and have a shareable information by all 3 machines, even within that room? How can we reach to this that later on can be shared across DoD and hopefully bigger image beyond that? Because if we succeeded to enable interoperability, then we are some of the first step towards the Industry 4.0. So interoperability and sharing information within the 3 system with one operator sitting in the same room, I think that will be the first step to a bigger one for sharing the data.
Go back to something that Eamonn said earlier about top down, right? I think that one of the biggest hurdles that we're going to have is being able to quote unquote sell this to the Navy customer, to the DoD customer, to the aerospace customer, whoever that customer may be, right? I believe that it's going to be one of the most important steps is going to be in truly defining what does that technical data package look like? What are the contents of the specific contents that someone can literally buy off and say, okay, I've got enough confidence in the quality of that part that I'm willing to fly it, float it, whatever the case may be, right? I'm willing to put that part into one of my vehicles or one of my articles. And I think that's going to take, I don't know, I think it may take a sense of urgency at some point. I hate to say that in a defense environment, but I think it may take a sense of urgency at some point for someone to be able to do that. The progression that everyone takes is from non-critical parts all the way up through critical parts eventually. And given the time and the money and the resources, that's a reasonable path to take. I think at some point that may need to get accelerated in order to be able to bring the model-based, computational-based qualification into reality.
Glenn, good point. Like next step, we're printing parts. That's the big thing. We got to scale up the use and get everyone comfortable with this and just get chugging along and get into production.
Yeah, and the guys have said it, right? It's about trust and scalability, trusting the process, trusting the models, trusting our sensors, trusting the validation that's gone into it, and taking things to scale, to no kidding manufacturing scales, right? So that's what I think the next step is. We've made great progress, right? This was built on a foundation of elements of nuggets from academia, from prior research, right? To be able to integrate it into a framework and to really look at how we continue to develop it, and that's both develop it internally within the Navy, right? As they continue, research and development, but also continuing it from the perspectives of industry and advancements of academia too.
And if I may leverage what Jennifer just mentioned, I have a question for you, Brandon. With all the information you saw today, do you think with all the infrastructure you have and the team members, do you think you can take all these 3 systems and leverage the millions of dollars spent by the Navy, deploy them within America-make infrastructure, and offer them to a wider audience, for example? Do you think we convince you that the solution offered by all 3 teams can be deployable within America Makes and the rest of your team members that possibly can help everybody else to push this industry forward? And please be as blunt as you like. We are not going to hurt my feeling, at least, just because I think you will be the first in line to say, did we convince you?
So I think, in short, yes. I mean, but to say that someone will flip the switch tomorrow and start putting parts in a system, there will be some degree of criticism and faith building that we will have to conduct in private, as was already said. I think, really what was just said in the last 10 minutes makes me feel confident in saying yes, because the things that Glenn and Justin and yourself have said naturally led me to the questions that I'm not going to ask, that I have written down here on the piece of paper, that is, how do we scale this to marginal or where we don't understand the value of the application yet, but we can extrapolate using these tool sets to understand how we augment quality, productivity, cost drivers, and get at those applications across different AM modalities. And we even touched upon another theme that the Institute's aware of is how do we make products by additive that don't lend themselves to the existing ways in which we certify products, or things that aren't readily inspectable. And there's a ton of value that can come from these tool sets to help build the confidence in those approaches. I was going to talk around that, but I think we've already hit on it, but I don't know. I mean, for me, those things are shining through here as the next steps. And I think I'd have to call that a success, because to lay the framework or the groundwork to enable people, the community, to take these next steps. And myself, I mean, granted, I have some experience in this space, but I mean, I think for me, it's clear, right? The physics, which is occurring, dictates our probability of success. So we need a means of ascertaining and understanding, which we use math to do that, hooray, and computers to understand that in a reasonable amount of time. That's what these tools allow us to do. They allow us to interrogate physics, which dictates our probability of success. And then we try to augment our probability of success by through design of experiments or virtual experimentation, so that we can get a strong North Star or a good compass. So
what I'll also say that is also really helpful, right, is that I think that a lot of these things, we can get to the answer, be it yes or no, faster, right?
Yeah.
Some of it is just you know, the answer starts with no, and then you got to build a whole bunch of stuff, and then the answer is still no, right? So if we can use these tools to kind of drive the testing that is necessary, and there's uniqueness of every application for those environments, right? And I would argue that can we use the information that's coming out of here to get us to the right question faster?
And Jen, on that, I think we're also now able to answer those more succinctly with data as well. Additive manufacturing for years has been as much art as anything else. You have to, when you have a new design, you give it to an additive designer, and they just kind of earmark it. Yeah, that can work. We'll just orient it this way. We'll put it on the build, and it shouldn't crash. We should be good. We now have more and more tools that are able to help us understand, like, yeah, this part might work, or maybe this one section doesn't quite work, and you go and redesign it. You accommodate for some of the limitations of the technology, and you understand where they are more easily and more repeatably. And it's about reliability and transparency around the process itself, whether it's the materials, the design, whatever else it might be.
yeah.
And, you know, Brandon, the other thing I would say is you asked, what have we done in the last 5 years, right? Where are we going? And I'll tell you the anecdotal thing that to me says where we've gone is that you used to be able to impress somebody by walking in and putting an additive part on their desk, right? And now nobody's impressed by that. What they want to know is, where's the data behind that part? And that's perfect, right? Because it goes to what Jim was just saying, what's the next question? The nice thing is that was the question 5 years ago. And now that's not even the question anymore. Now they want to know, where's your digital twin? What's the computational models? Where's your simulations? What's your MLAI on your process control, right? So they're asking those questions. So to me, it says that in the last few years, we've headed off in the right direction, because they're not asking where the data is anymore. They know that nobody brings a part without bringing data nowadays. So we must be headed in the right direction.
Yeah. I'll do a few questions here from the Q&A, and then we'll probably be pivoting into a networking session. So I have a question here. It asks, it says, what Icme methods can we use to go from building a standard wall or cube to predicting what processing parameters and microstructural transformations would occur for a unique geometry?
So I'm going to jump in first because I think the other two guys are better slated to answer this than me. So I'll get out of the way. In my purview, that is the Icme tools, right? I mean, that's what they're intended to do, is to be able to take simple geometries, make sure that your model works for simple geometries, and if you can predict in my case for TIE 6.4 at least, if you can predict the thermal history accurately, then irrespective of those the more complex geometry, you should be able to come back and show that either through in-situ data or through modeling that you understand what the thermal history is, thereby you understand the material state and therefore the mechanical properties in that complex geometry. Again, the value in that is being able to have people accept that Icme is accurate.
Yeah, at its heart, I mean, what you need at the start of the Icme type of simulations to understand the material impact is the as-built material quality, as-built microstructure, and that's primarily determined by time and temperature. How fast do you cool in a region? And that can differ between regions. Bulk regions of a cube versus an overhang, they're going to cool differently. But we have simulations that can predict that now. And so we can get those strike level insights that really allow us to have succinct understanding of what's happening in that process. And then we can understand and extrapolate what that repercussion is all the way through all the heat treatments to your final material quality. And that really drives home a way for us to iterate more quickly and converge on ideal solutions.
And if I may add, that concept that we just raised related to location-specific heterogeneity and implementing Icme for location-specific heterogeneity in wrought product is nothing new. This has been done in the forging industry for a very long time. You use a finite element with UMATs to predict location-specific deformation gradients that you are able to predict with the temperature how your grain structure looks like. And in fact, this is even some of the processes to qualify parts through the supply chain of rotating engine components. So I think in certain areas, additive manufacturing is mistreated and it just treated with a more bigger magnifier glasses than wrought products. Like when you look at the forged pancake, there is a huge heterogeneity in it. And this is also still being developed and monitored with an Icme infrastructure. They just call it finite element simulation with user subroutines. So I think we have the groundwork in the wrought. It's just we need to forgive additive manufacturing to being the young kid in the block and accepting that casts have porosities in it, accepting that cast material have heterogeneity on the microstructure, accepting that even wrought has some problems with it, and just additive is just a new name for a very well-known process used for a very long time. Sorry, I just feel that we always getting picked on just because we are just using the new technology. I'll step back from my soap opera.
That's pretty typical for all new technologies that come on, right? Is you get a lot of extra questions. And what I'll say with respect to this particular question and what maybe you didn't see in the presentations is the body of work that they all built on understanding microstructure and processing relationships on simpler geometries to dig in deeper in those more unique geometries. The demonstration articles was a key component within Quality Made and was very specific within our option phase for demonstration of a part, right? A Navy relevant part. So they all just kind of cut to the chase of the coolness of the parts, right? But they spent many years building out that framework to be able to manipulate it and exercise through it for a demonstration article, right? And each one that they do makes them go through the framework faster. So just a comment.
No, I think that's exciting. I mean, to hear what came out of these efforts, right? I think there were a couple of things in terms of the key performance parameters or success metrics that were talked about. But, you know, one that sticks out to me, I think Justin mentioned something about 50% of the effort that went into qualifying a product could be saved thanks to the development of these tools. And I mean, that's this go around. And there's not just one part number that could be applied to, right? So, I mean, to think of that and how that could be extrapolated or compounded across a product portfolio, that's considerable. That I would dare say significant. And so, I mean, that says a lot to me. You know, thinking about long-term value, and piggybacking on some of what Eamonn was asking me, I guess, how do all of you envision this more or less transitioning or evolving out into the supply chain? So the evidence is here, right? The work is done. How do you see folks utilizing these tools, efforts, and disseminating it into the lower tiers of the supply chain as well?
So again, I think the other two guys are more qualified, so I'll jump in first. So what I believe is that so Lockheed Martin is, you know, we're not a manufacturer of components in general, right? We're a systems integrator. Most of what we do is procurement of components and then the assembly of those into complex systems. But we need to be a smart buyer of those components. So what I believe is it will happen within this supply chain is that there will be requirements levied on the suppliers to be able to show that the processes that they are using, specific processes that they are using on specific machines, et cetera, are able to meet the part requirements, functional and performance requirements, based on using these simulations to predict the part quality, right? So we'll go back to our models, use what the specific manufacturers are doing, and saying, yea, verily, we can qualify that supplier based on using his parameters, his set of parameters, whether it's process parameters or scan geometry, scan strategies, and say, yea, verily, when we go back and plug these into the models, this part meets our requirements. That's the way I see this flowing through the supply chain, right? And in addition to that is that I believe that there will be some additional in-situ process monitoring that gets levied on the supply chain. Because in my humble opinion, that's the way you're going to convince the customer that you have control of that process, is by being able to conduct that in-situ monitoring of, depending on the materials in the process, but mainly of temperature and the geometry of that melt pool, et cetera. So that's the way I see this flowing in the supply chain, is that they'll have to meet a set of requirements that are essentially defined by these simulation and computational tools.
Yeah, that's a great point. Requirements is what this is all going to come down to. So the additive industry is going to and has already started adopting some of these technologies. Credibility has been building around this type of capability, and it's not going to stop. You know, thermal simulations have been coming around for some time now. Icme simulations are now getting more visibility and buy-in and capabilities shown, and it's building up with sensors and others as well. But at the same time, it's also around the user now being more knowledgeable of what's actually needed. So when you want to have parts made, hey, I want to see what the melt pool is actually doing in the build, or how to provide us with this material data set. And you know, these requests are going to start extending beyond what's experimentally feasible. You're going to need to have simulation to really drive some of these points home in a cost-effective and time frame reasonable way. And so, you know, we see this coming through from both a user standpoint and a machine OEM standpoint of this convergence of what the right data sets are. And that's really driving towards the integration of these technologies into the industry pipeline.
And to leverage the comments from Glenn and Justin, speaking at the smallest company in the attendees here, and we are trying to offer to Lockheed Martin, GE, as well as the Navy, those users in the supply chain by pushing for distributed manufacturing. And with that, we are working on the Icme tool we developed. The Icme is cloud-based, working cloud computing that the various companies can work on it, as well as it doesn't need a PhD to run it, and try to work with different machine suppliers to try to train it on their machines. So we are trying to take the steps from the small business perspective, how we enable multiple users that they don't have millions of dollars to invest. They can hire one PhD, multiple engineers, and a lot of technicians. How we can enable them to use an intuitive approach that can run in a tablet or a laptop, that we provide to Lockheed Martin or GE the information they need to provide to the Navy the final solutions. So we are trying slow by showing how can we share the data through a well-structured cloud computing browser-based, and then hopefully working with different suppliers of machines. We are not making machines, we are leveraging application programming interfaces with those machines. And hopefully we can reach to this data package that will be required by getting a lot of people to use it. So whatever we can get a lot of people to use it, knowing now if you have $500,000, you can be a manufacturer. You can buy a $500,000 small machine, and here you are. You can build metallic parts with $500,000 to $1 million. This is sometimes within the price range of a small house. So distributed manufacturing is what we are trying to do to offer to GE, Lockheed Martin, and the Navy some of the solution and other companies.
Yeah, that's a really good point, that it's around the scaling of technology. I mean, as additive is really driven to more and more adoption, everything that we've been showing today between these three projects are almost required to really start making an impact in the industry itself, and to let the industry meet up with demand. But even more so, it starts allowing us to push additive even further. You know, we are living in a world where bigger parts, more complex parts are being constantly designed and really pushing the technology. And we need to have this type of understanding and capability, the material quality and the material and the print capability, to be able to really champion these new technologies, these new geometries and applications of additive manufacturing. And what we have now is a suite of technologies that are being pulled in by the industry that are helping accelerate and adopt those new types of use cases.
I'll say is as industry is looking to adopt these technologies, right? We, as a customer, have to be able to understand what it is that we're looking at. What data are we going to need to have? How do we navigate through these processes? You know, I talked at the beginning about really changing that qualification paradigm, right, within this framework, and I think that as industry begins to really adopt this, we have to be able to respond to that.
Yeah, that's great. So we're pretty much out of time, but I think this has been tremendous. I want to thank everyone here, Justin, Eamonn, Glenn, Jen. Thank you for your time. Thank you for sharing this with us today. These discussions have been excellent. Thank you so much to our audience, our membership, and especially our sponsors. We're gonna go into a networking session. I think this platform will be available for us to all kind of continue chatting with one another for about the next half hour or so. And thank you all for your attention. This has been great.
Hey, I did have one. I had one last question for Jen. Did you intentionally go out and find 3 bearded bald guys to do this?
To be fair though, like some of this came upon via COVID, right? Like
I was just curious. Yeah, kind of struck me. That there was a similarity there.
I think it's Jennifer demanding of the work we do. I think this is an immediate outcome after 40 years. We have to fulfill her goals. So it ended up losing the hair, and I have no time for beer.
No time to shave. That's exactly right. Yep.
Oh, now I'm gonna get a whole like reputation about this too. Coincidence, I swear.
All right, we'll take that.
Something for me to work towards.
Yeah.
Enjoy the full head, Brandon. It's okay.
Yeah, the beard might be a little tough for you, but good luck.
Yeah.
Again, yeah, thank you, Brandon, for putting this on. I really do
Absolutely.
appreciate it. Yeah, thanks.
Yeah, and thanks
you,
for the
Brad.
whole
Thank you.
America Makes team. It's run so smoothly. Special shout out to Tara and to Todd in pulling this all together.
And I guess to the audience members, I mean, we're gonna have this Q&A afterwards, but after this all wraps up, feel free to reach out in the coming days and weeks. I think I speak for Glenn and Eamonn as well. This is all about connecting, building out a network from this. So reach out, email, call. Happy to talk about all this further.
Yeah, no doubt.
I echo Justin's comment, not just for the audience, for Lockheed and GE as well, and Brandon. We are happy to work with all of you, and as well as the audience. Thank you.
Thank you.